like if you can just make you just show somebody else if you've done those Arduino tasks. So it should probably take a computer engineer half an hour. If you've never done it before, well, then it's a lot of YouTube videos to watch. And then there's a big emphasis on user testing and usability. So like if you want to build something like an interactive keyboard or something for like say a smartwatch, how do you know if it's actually any good? Like you as a designer will go, as an engineer, make all sorts of assumptions, and then you give them to humans and they do anything they want to do with them. And so there's a lot of learning to do in that space. And then we go and build a major, final project basically, which is most of the class. And we read lots of papers. We understand the state of the art in the field of ubiquitous computing and mobile systems. All right. You guys can jump on that. You guys are excited about digital to analog converters. I know. I'm excited as well.
The less complex version. Stuff that's in stock. It's just the blue. And then the speakers. Yeah, that's what they said at the meeting. Because that's what they said, don't make the custom wearable. That's because we already have first minutes then just.
Okay, let's see. Wow, that's very loud. Okay. Homework was due yesterday. Project proposal resubmissions are due today. Just do me a favor and just like make a new copy and write revised in there. So if I go and look through, I'll be like, aha, that was the thing. That's the thing I should look at and not the other one. Now, if you don't change the title, then I don't know if you did it or not. So if you're in the situation where like, oh man, I already updated my thing, I don't know what I did. Google Docs has history, so you can just roll back to wherever, make a copy, roll back. Your state is all there. Student presentations are coming up, so all the topics are up. You guys can go sign up for review slots here. I put a link. So those are all the slots that me, James, and Matt have made available. You'll basically go give the 12-minute talk to them, to one of us, and we'll give you feedback scheduled for half an hour. Approximately here are this group of people has to sign, or the people presenting here should probably sign up in that block of time. You guys can fight for the times. If you really can't get a time before you're supposed to present, let us know. We'll make extra time for you. But there's more slots. There's 31 slots. There's only 21 groups. So you should have plenty of availability to find time to meet with us. Yeah.
This review is like after we actually make the presentation. This is like a practice run.
Yep. We're helping you with your presentation skills.
Should we also try to meet with you guys, I guess, once beforehand to figure out that we're planning on presenting the right stuff, or should we just
if you have questions, definitely you should. But some people are going to be like the Pixie camera. Pretty straightforward. Some of them, my one-word description was probably vague, and she just come and meet. I will actually probably have extra time today because I don't want to start reviewing for the exam yet. So today is a good time to talk about that. What other questions do you have? Yeah?
This is slightly unrelated, but if we happen to want to change something in our project, once we start working on it, do you want us to go back and revise our?
No. You should talk with me, Matt, and James to kind of make sure that all makes sense. The purpose of the revision plan is really for you to be this is exactly what I'm going to do. And have that time to really think about it and this is the part number, and make a concrete plan before you go forward. And it's me and Matt, James' job just to make sure that you're doing that. Now, it's not a contract either, so I don't, if you change something, that's fine, so you don't have to go back and edit the proposal. But yeah, definitely check with us. It could be the case where somebody makes a change in their project that basically makes it so simple it becomes trivial or something, and you're well, you just lost a whole bunch of points, so we'll help you with that. That's a good question. Any other questions? Okay. Last homework assignment, due Monday. And then on Friday of next week, not this week, next week, we'll have the midterm, and then we'll do midterm reviews on Monday of next week, and then we'll have our last lecture, formal lecture of the class on Friday, or Wednesday. Okay. After that, student presentations. We'll have a guest lecture from, I forget what company, but a company that works in embedded systems in the area will come and give a guest lecture. This is a good opportunity for you to figure out like what does embedded systems look like out there in the real world. You'll hear about what they do. At least you can shake a hand of an actual engineer and be like, okay, maybe you'll hire me. That's not a bad thing. If there's time, I'll also talk a little bit about if you wanted to go the other path, which is like graduate school. What the heck is that like? What do you actually learn in the PhD versus what you learn in the master's degree? Okay. So today we're going to finish up DACs. There's the reading. Okay. So let's see. We went through, got here. We talked about loading effects, basically, just as a quick review. To avoid the voltage divider problem where source resistance will corrupt your signal, you put a buffer in there. Great. And then you're going to see a whole bunch of DACs that I've built in Falstad, and I forget to put the buffer on all the time. So you can just envision there's a buffer. If they want to make it correctly, you put a buffer on the output so that you would avoid the loading effects. Does anybody have any questions about loading effects or why this is a problem? Yeah.
Briefly answer both of those.
Sure, that's a great question. Okay. So the challenge here is when we make electronics, when we use a power supply, it provides a lot of current, right? It's great. And when we have our little symbols here, like just a voltage symbol, it provides infinite current. But in the real world, unless you pay a lot of money for that test bench instrument, it's going to have limitations in how much current it can provide. And the effect of that is that you have an equivalent of source resistance. Now that source resistance may only be like a couple ohms, maybe 10 ohms, but sometimes it can be more substantial. And the loading here will cause a voltage drop because this is making a voltage divider. Does that answer your question? Okay. So that's the challenge we're trying to overcome. And the easiest way to do that is just have an output stage, which is an op amp. And the trick with the op amp is it provides no current can go into this positive node, right? It's just basically sensing that voltage. And then this topology of this particular op amp is a follower and basically says whatever the input voltage is, I'm going to make it over here. So now this device has very low output resistance. Maybe it's only 10 milliohms or something. And so now it can drive this load pretty easily. And it has a feedback loop because trying to always keep this thing at that low voltage level. Yeah.
Explain how the mirrors be desired and there's no voltage drop across.
Somebody took 215. You guys learned op amps? Okay, so you guys can correct me here. Okay, let's see if I can remember. I've got an op amp here, right? This feedback loop is trying to keep the voltage difference between those two nodes 0. It's going to constantly adjust the output such that this would somehow keep that 0. So if my voltage in is 5 volts, it's going to change this voltage such that these two things are the same.
Isn't there still a voltage drop across the resistor?
Yeah, sure, fine. Oh, why isn't there a voltage across the resistor? V equals IR, right? So V equals IR. So this is the voltage drop across the resistor, not at a point in the circuit. What's the current through that resistor? 0. The input to an op amp is high resistance, high impedance. It's supposed to be mega ohms. So now my I is 0, or effectively 0, right? Therefore, my voltage drop across the resistor is 0.
Going through the capacitor.
No, so I will erase that capacitor. Let's just say in the steady state, right, we're at low frequencies. The thing that always boggled my brain is that at higher frequencies, capacitors turn into shorts. Damn it. All right, but this is gonna say this is low frequency, so now, yeah, it's just buffering that thing. Yeah.
So in our STM, whatever, they said something about the buffer. Is the buffer just the amplifier itself?
Yeah, basically.
Same thing.
I mean, I don't know where there's a lot of things in the data sheet that have the word buffer on it, but if we're talking about a DAC, yeah, there's a buffer.
Okay.
Okay. Did I screw up anything on the, oh, good, I still know op amps. Enough to fake it. Okay. Any other questions on loading effects? What we're worried about here? Okay. And the thing that might not be obvious is sometimes these loads are actually pretty large. Like 10 kilo ohms, probably not that big, doesn't make that big a deal. Maybe that's like the input of a GPIO pin is around 10 to 20 kilo ohms. It's pretty large. But like the output of the input resistance of a speaker or some LEDs can be pretty large or pretty small, consuming a lot of current, and that's what causes the problem. All right, and then there's a false side there. You can play with it. You can wiggle these things around. It's fun, I promise. Then we talked about the most basic DAC, which is super simple. You could make it. If you didn't have a DAC on your microcontroller, you could make one of these. Right? All you have to do is you have your output PWM pin microcontroller, put an RC filter on there. You can use a nice RC filter calculator or calculate it by hand to figure out what the cutoff frequency should be for your particular pulse width modulation, the frequency of your pulse width modulation. But it will allow you to go through and it will filter out those rises and fall. It'll filter out the high frequency components, leaving you the average of the signal that you see. So this is probably a better example. Here you see that the average is very high, right? We're nearly 1 all the time, maybe it's a 1% duty cycle, and then the voltage output is low or is high. And then here the average would be closer to 0, and now the voltage output is 0. The problem with this type of DAC is that you always get these noise in here. It's very hard to get that ripple out. You could put a second order filter, a third order filter, but at some point it's just better just to use the correct filter or use the correct DAC, I mean. Any questions about this one? Okay. And there was good false out if you want to see that. Now, we didn't get to the voltage divider ladder, correct? All right. So kind of building off of the same structure that we had for the flash ADC, we can go through here and make a representation of all possible voltages that you could want. All right, so now I go through and the trick here is that you typically always use the same resistance value. That means the structure they make in silicon is all the same size and process variation should affect them all about the same. So that gives you relatively good linearity. And then you just have a switching network that selects the one that you want. And you probably have to have a buffer on the output because you imagine that here, from the reference voltage here, there's a lot of resistance in the path. So this would actually have a lot of huge source resistance, and that's why you need to have that buffer. What questions do you have? Yes?
Does the buffer serve to like amplify our thing because we lost a lot due to the resistors?
It doesn't amplify it, more, no, it doesn't amplify. Let's look at this one and then it'll answer, then ask your question, okay? So let's see, is this one running? Yeah. So it's super simple. I have this ladder here, so it happens to be 7 volts. Clearly on your microcontrollers it would be different, but each one of these voltages you can see down in the corner, it just sees what the highlight is. It's stepping it down. And then you just use a binary encoder or some sort of network. So here's a bunch of link switches, and I can go through and digitally select. So here's a digital value, and I get some analog value out. Now the problem is if we go and put a resistor on here, let's go and do that. So that's wire. So if I connect this, it's dropped that down. Right now it's drooping. It's because all this whole path now is the source resistance. So whatever that is, 500 ohms of source resistance divided by the relatively high impedance of a kilo ohm, right? So this voltage divider that's made has dropped that voltage down. It did want to be 2. That was a desired output voltage, but it couldn't make it. So now we should put that buffer in here to overcome that issue. Did that answer your question? Yeah. Oh, whoever's. Both of you are so close together, you might have the same question.
Oh, no. Did I answer your question first? Yeah. Okay. I'm just curious if you're able to explain briefly, how do the op amp maintain the output voltage? Does it have a different source voltage something like that?
Yes. The secrets, we didn't show you it. Yes, op amps, let's see. Yeah, they're magical and we didn't show you. But yes, op amp has VN and VD in ground, and then, I don't know, a couple hundred transistors, and some magic occurs. That's like an advanced, that's a 400 level analog circuit design course, which I took and promptly forgot.
But it does have a different source voltage other than what we can see here. Is that correct? There's 2 more wires coming in and out of it that you just didn't draw?
Yeah, so in this case, you're probably going to set the op amp out to VREF, and then it's going to the negative rail is going to be ground. And op amps in general, some of them can be specially designed to go rail to rail. They can output a signal. Sometimes they have to have a voltage drop, so you might have to have your op amp be higher voltage and lower voltage than the actual signal you want out. All right, any other questions? All right, so this one, make a voltage resistor ladder and just select what you want. Okay. I didn't go and make pros and cons lists. Oh, that's sad. So one of this is nice because all these DACs are actually pretty fast that we're going to see today. The voltage is available immediately. It's not like the slope integrator where you had to do something over time. The pulse width modulation, maybe you can make an argument that it has to take some time because you have the low pass filter there. So this one's done immediately. It just costs a lot in terms of area, resistors being large structures, and you have to have a resistor basically for every voltage that you want to put out. So that's a disadvantage. We'd want to figure out a way to get less resistors out of our DACs and see to make them smaller and more cost effective. Okay. And then I think somebody asked it maybe last time, what happens if you did more than one switch at once? I think they were asking for the ADCs. Oh, I can make this like this. So that comes into a building block we have to think about, which is a summing amplifier. Now your analogs brains are totally in panic mode because you have to learn what this thing is. Basically, the only idea is here, whatever the current's going into it is going to sum the currents and have a current on the output that's proportional. We can use that, or we can use the resistors to turn the currents into voltages. So all the circuit's going to do is going to sum the voltages, okay? And that trick, basically taking currents in, summing them together and creating an output voltage, will allow us to reduce the number of resistors. But let's first get an intuition about how this works. And now I realize that this may not be the easiest simulation to see, because this is just the default summing amplifier from Falstad. But basically, we're showing you one's a sine wave, one's a square wave, and you see that this is a summation of those two signals here. You'll notice that summing amplifiers actually have a negative output, so it's these two things times -1. We're going to ignore the fact that all the summing amplifiers you'll see have a negative output. You can just trust me that through analog trickery, we can turn that back into a positive number. And you probably don't want to learn all that trickery, okay? But just believe me, it can happen. So the big takeaway is I have two currents coming in to this negative node, and the output is a summation of those two currents. And that resistor over there turns that current back into a voltage. Okay. So one of the more classic versions of a DAC is the R2R ladder, R2R ladder, which basically, this looks horrible, fantastic, which basically makes a network that distributes currents in a fashion where you can do summations of those switches. So you can have more than one switch. So you have a current here that's a 16th, a version of the current that's an 8th, a version of the current that's a 4th and a half. And then because it's a summing amplifier, you can add a half to a 16th to get a summation of those currents into the op amp, and then the output resistor turns it into a voltage. So this allows you to hear your switch coefficients here. You can turn those switch coefficients on and get a voltage output, which is a summing factor. This allowed us to have less resistors than if you had to make a voltage ladder. Yeah. What's the difference between smooth and square waves? So there are two different signals. So we have a 300 hertz sine wave on the top that is going into the negative node on the op amp, right through that resistor. So you got a summing node, and then we had a square wave. So these are the two signals. Do you agree? That's the difference between those two? So sine wave here, square wave here, both going into that node. This is the output. All right, we can do it this way. That one's that one, and then that one. Yes. So it's the topology is a summing amplifier topology. So it's cool. You can do some analog signal processing. You can sum two values in analog. Yeah.
It's not direct sum, is it? There's like a coefficient of the output.
Yes. Yeah. But we're going to choose our resistor values nicely, right?
Oh, okay.
So that happens to all those values are the same, so your amplification factor is 1. However, you're right, if you wanted to, you could change the output resistor there, and then you get a summing amplification. Yeah.
Why do you need the op amp here? Because it seems like you could just combine the two signals into a wire and it would produce the same output.
So if I add the two signals into a wire, I don't think that's going to work. Then I'm going to have a short circuit, and then I don't know what's going to happen. Like, I'm going to put a load on that, and then it's going to defeat it. It's going to start sucking off some of the current. So we have a loading effects, and then current and a current. I guess you could put two currents in series and add them. No, two currents in parallels. I don't know. It doesn't work. You need this thing. I'm not an analog circuit designer. I work in HCI now. Geez, you know how long ago that was?
So wait, the op amp just serves so you're able to see the output without shorting it to ground, essentially? Is that what you're trying to get at?
I don't know. We can sit together and we can draw circuits together. We'll take that as a exercise offline, but I do not know of any other way you can sum two currents together without this amplifier, without some negative effect I can't think of right now. If somebody has a better answer for me, feel free to jump in. Okay.
I also have another question.
Oh, good. Yeah. Let's see if I can get any of them correct today.
For the R2R ladder, you said there were less resistors.
Yep.
I don't fully see that because in the resistor ladder, like it seems like you have the same number of resistors in the ladder, but then you have the additional resistors coming off of the ladder. Do you see what I mean?
Yeah, I saw what you mean. I think as it scales, it gets less. I don't know. All right. In this case, it has the same number of resistors. Let's say that. I don't think it does. It has per bit. Let's see.
It scales logarithmically.
Yeah. So I think as you scale it, you get better results. Yeah.
How did we get the formula for the R2R ladder?
What's that?
How did we get the formula, the V out formula for the R2R ladder?
How do you get this formula?
Yeah.
You go back to 215. We can take it as faith, we could derive it together, but basically if you try and figure out the transfer function, this is what it is. The trick here that's not obvious is that the S factor here is going to be 0 or 1, and that's just the switch. And so we're saying we're going to take the summation of the currents that are switched on, so R1, this one, and this one. Oh, maybe this should be 4, and that should have been.
That's what I was.
Okay. Thank you. I'll take that as a note. Ooh, I can change it right now. Then I don't have to do anything later. And I need a fourth one, a fourth term anyways, I think. All right, well, I'll take that as a note to double check that. Okay. Let's go back here. Turn this guy off. And so you can kind of visually see the summation of currents here coming in. Yeah, so basically you get a binary value here. In this particular example, we're getting a negative 15, positive 16 up here. And so this is inverting it, the signal. Again, we'd have to do analog tricks to basically make it a positive value, and you would prefer not to have a negative rail. So this op amp secretly has a negative rail of negative 15 volts and a positive rail of 15 volts, which just in practical terms, you don't want on your microcontroller to have a negative rail. So you would do more tricks to make that all ground to 3.3 volts, and then you would invert the signals with a little bit of gain to get it back up to the full scale of what you're looking for a DAC output. But anyways, what questions do we have? Okay. All right, and the last one is, I wonder if that equation is correct. I think it is. So last one is a binary weight ladder. Before it was the scaling allowed you to have all the resistors of the same value, or two different versions of it. So you had a resistor one of value 1 and a resistor of a half of that, which was very nice from a manufacturing point of view. So now you, so like in silicon, you basically lay out a resistor as usually it's just a functional block, but like poly or as a serpentine metal structure, and then you can just make clones of that, and it's easy in a sense to make sure that they're all the same size. You'd lay them out to be the same size, and you have some that are double, like you just wrap them around. And basically, in silicon, you're trying to make the resistors all the same size or multiples, so that you have, when you go through process manufacturing, that they all are changed similarly, right? So if they're all a little bit smaller resistance, you want them all to be even. So that's great for the voltage divider ladder and the R2R ladder structure, but those cost you to have a lot of resistors. So there's a way to get around that where you have a binary weighted resistors, but now you have to have more resistor values. And it makes your layout more complicated, and you're more prone to process variation skewing some of those bits. So all of a sudden you could have a scenario where, R divided by 8 isn't an evenly divided by 8 value. It might be like 8.1. And so that would corrupt, whenever you add in that little eighth of a bit, it might corrupt your output a little bit and not making it nonlinear. So that's why this is I'm just trying to prove the downside of why you wouldn't just go for a binary weight resistor DAC. There are times when you might want the other DAC structures for linearity point of view. But anyways, the big difference between this one and the last one is that now we're going to choose resistor values that allow us to have a binary weight. And if we go to Volstad, it's a simple design here. We're just seeing these values, and for every bit you're going to have another resistor. So the growth as you scale this up is pretty good, and then you're just adding these currents together. Yeah.
In that diagram on the slide, was it the VREF listed as negative just because when you throw it through the inverting op amp, it just kind of comes out positive?
Yeah, exactly.
Will you safely just always assume that we're going to get a positive V out, like if it was a test question or something? Or would you try to trick us by being like, oh, you didn't get that it was inverting, you should know that?
I am tricky, but I don't think I'm that evil.
Okay.
Because I rather trick you with embedded systems questions than analog circuit design questions. Yeah, I mean, it's unlikely. I wouldn't ask you in a test question, hey, design me this particular op amp structure or DAC structure, but I might say, what are the trade-offs between this? Or you're given, I don't know, you're given these requirements, which one would be the best one to use? Yeah.
Do you mind explaining again why we need the op amp at all? Like, wouldn't this kind of
This one works, this one is fine
without?
for loading, but the problem is, look at this output voltage, it's negative. Right, so my ladder structure here has positive voltages going in here, so here's a binary 5 volts, I assume. This is, 5 volts. So positive 5 volts in here gets inverted in the summing amplifier. So now I have negative 15, and there's a little bit of gain on this thing as well. And so don't worry too much about it, but if you are, looking at this and being like, well, my little microcontroller is not putting out negative voltages, how could this possibly work? I'm just pointing out that you would need a structure after this to reinvert the signal to make it a positive voltage, so that your your microcontroller would give you a digital voltage between 0 and 3.3 volts. Does that make sense?
Just like, I guess just to explain why this is wrong, like why couldn't you just have like it go straight out and like without that whole?
Why don't we have it? So that wouldn't that just be this thing? I think it would be, it seems like it's about equivalent, right? And then the challenge is, well, now I have to have lots of resistors. And so those tricky analog people are trying to get rid of those resistors. And only because resistors happen to be big in silicon, that's why. Otherwise, nobody would care about this problem. They just use all the resistors they could get their hands on. Yeah.
If the inputs are 5 volts, how does it go to 15?
So remember, there's gain associated with this. So this resistor here is giving some gain to the signal. And this particular thing has negative and positive rails for the op amp, right? So in this case, let's look inside. Yeah. The max voltage for VN is 15 and negative 15. So, yeah. Does that answer your question?
Yeah, so if you change the min and max to like 10 instead, the output would be 10, or negative 10 volts.
It would get saturated. Let's do that. Right, now it can't get lower, just because the negative voltage rail can't get any lower. So this would mean that you're trying to drive this digital value to something, and it just can't get there. Does that make sense?
What is it? So if you increase it like 100, it wouldn't be 100?
No, this is just the input supply. So it's back to 15. So the gain factor here of summing all those currents and then giving it some amplification, turning the voltage or the current into voltage through that output resistor gets you a value of 15. And so we could sit through and walk ourselves through those equations. The op amp rails, negative and positive op amp rails, just tell you the maximum voltage or maximum negative voltage that it will produce.
Okay.
What other questions do you have? I don't know. You guys give me the looks like you know what's going on, but your eyes also say I don't know what's going on. Okay. All right. So I think the big takeaway from the last 3 DACs is the goal of reducing resistors. That's it. All right. What else should you know? We'll talk about this more in a second, but I might as well talk about it here. It's important to recognize that DACs, just like ADCs, all have quantization error, right? You want to go and have a little value that's in between. You might want to get, in between a bit, but you're not going to be able to reduce it. Or say another way, you want this nice pure sine wave out here. Oh my gosh, that would be so great. But all you get to do is these steps functions. And so just recognizing that that is a challenge is important. It's the same with ADCs. Okay. So we'll go through and, oh no, you guys are going to be so disappointed. I left your worksheets upstairs. You guys came to class for nothing. This is horrible. Oh man, all right. Well, you guys can just sit there and work on a piece of paper as we go through this experiment here of coming up, work together for like a couple of minutes, come up what you think the relationships here are. So I gave better instructions this time of high, medium, low. Here it's important to try and calculate the number of resistors you need resistors and switches as a function of the number of bits. Yes?
Are we turning newspapers or kind of?
No, you don't have to turn them in. That's a fair question. Just go through the, now we're just learning for the experience, not the credit. That's sad.
Separate plan, you have to pay separately.
Yeah.
Like we're back of the same size, like number of resistors. Basically.
Yeah. Let's say physical size.
Physical size.
Or which one is more likely to scale to larger resolutions?
In the slide before, where we were showing the quantization error, what was the blue plot for?
Let's just show the error.
Error, right?
To the error. So here the desired is this, and the error got larger.
Why does it like
The magnitude of the error.
Notice, so.
Green is the desired, red is what you did out, and there's the magnitude of the error at any one point.
I think at the top it's pretty high.
Yeah, this line, it's a magnitude, this, so there's
Oh yeah,
negative
it's a
error.
negative too, yeah.
Yeah, so that's green is big, yeah.
It's yeah. For that one. Although like dude the resolution is always like
You tell me. Oh man.
PWM plus LPF.
So like 216 or
okay, so resolution.
Oh, I guess we do. I feel like it's relatively good though. Green PWM.
Resistors, which one is more likely to have mismatch?
What's the difference between
You inherently are still outputting discrete values based on the number of
like it drops by like if you have 4 voltage divides, it drops by n over 4.
Translation.
The same
Resistors.
resistor.
Average. Yeah, I think I agree. Let's say medium.
it's either low or high. I don't know.
Medium.
That's a big difference there.
Yeah, I know.
That's my first thing that was fine.
I'm curious how we're interpreting. Because I could say
It's all just analog circuit. So you need to actually write the number.
our op-amp is fast. Still only output discrete values. Like you can't.
of these 4 types of DACs.
I would say end of the end. So I could say like I could feel the
There's a question there of like how do you make this decision? Because you're actually using time
you can, but
RC filters limit your resolution too because you have this very
time to go.
You need an op-amp on both of these, so that's pretty complex. So it's
I don't think so.
They all have
Because it's this one.
Maybe but comparatively like
if I'm trying to make really big
Like the picture for single
I think that's pretty simple because it doesn't have as many resistors.
size I can get like for this amount of size I can get a lot of resolution like pack in the resistors and each one of those resistors.
You know how to write parallel. Your entire group is
Area has pack in resistors I get less resolution.
mashed out.
Like make yourself do the entire core function.
There is also one that's called
I would think so. It has to.
So
Maybe we'll probably have a
Sliding from the side, or maybe like a sugar.
This is not about like, this is about like,
We're doing like
we're not gonna grade you anymore, you'll be out there in the real world.
that's we had to care of like scalability.
I was thinking of more like, given that you got variation a lot, I can guarantee you it's different to
Lighter.
variations.
Curve's gotta favor somebody. Curve's gotta favor somebody.
All three of the next ones have an op amp.
Fresh exams are gonna take a swing. It's all just everything. I already took over the TUF.
every single 73. Because I was like, oh, did you understand what linear?
That class is so much harder than this
Cool.
one.
Let's get a high five.
That's true.
Okay, so 0. Does it have one resistor for the completed?
There's a thing in like industry where like
You know, Ava, I have a question. Since I'm clearly not gonna understand this, I'm curious if you could explain the last few slides of this, because I what is what is this?
I'm sure he did. I'm sure he went over it. I'm just sure that I didn't. I cut off at, see where I cut off my understanding.
Yeah, you make a budget, then you gotta use what's in there.
Here?
2 to the power of
So maybe this didn't go over.
that many levels, essentially.
2 to the n times 2 to the n is your count resistors and resistors.
He eventually posts a video.
The last video we posted was 11 days ago.
Hey, let's see what we come up with. I also realize some of the definitions are vague. That's fine. Work through them, think about how the trade-offs. So what do we think for the resolution? And the part I probably didn't give you was I feel like it's resolution given the same amount of area. Right? Area constrained, which one would give you more resolution, or which design inherently has a better ability or scale better in terms of resolution? So what do we think?
PWM has best resolution.
Okay, now let's come back to PWM. We can debate that one. That's gonna have a lot of arguments. What about the other three?
Binary weighted because it has the least resistors.
Yep, and then,
Oh, and then the
that's right. I think I put this one in the middle. I'm not, when we get down to here, we can see why in a second, but yeah. Okay, so what about PWM? Does that have good resolution? What's the factor that defines resolution here? Yeah, so this is nice in the sense that you're not defined by some physical quantity in the sense of, like, did you put enough resistors on? You could just up your clock speed and up the resolution of your pulse width modulation to get more resolution out there. So that's nice. What's the drawback of this design, though? What might limit what we would think about as resolution?
Speed.
What about, okay, that's true. Let's see if we go back over here. What about this jitter here? You don't think that's a huge problem? Anybody think that's a huge problem? Back me up here for a second.
It depends on like your filtering, like just this alone is pretty bad.
Mm.
Then you don't really get what you want. But I don't know, maybe if you can throw like a solid key or some higher order filter, like maybe it'll average out to be okay.
Oh man, now you went all analog on us. Let's see, do I have that one booted up? No. This is probably good. Johnny. So I guess my argument about maybe why resolution isn't perfect, because if I have this variation, yeah, I can make the average, I can use more time slices to make the average very precise, but I'm still gonna have the ripple on top. So it's like you get this losing battle. I get millivolts of resolution, but I have hundreds of millivolts of variation. That wouldn't work out well. So it seems there's some conceptual limit on that. But yeah, so it's in the mix of, I think there's a cap on resolution. Okay. So what did I say? I don't know. Could have said something. So I said medium, but I put a star there saying it's based on time, but it's noisy. So we get the benefits of time, but there's this noise. I said that's low, medium, high. I had to guess. I was thinking more as you go beyond, as you increase the number of resistors, or bits. I think that's how the thing comes out. What about speed?
Said the voltage divider was high, and then the other two were like medium high, medium low. Like the R2R ladder and the binary weighted were like medium high, medium low, because you have to wait for the op-amp to do like the feedback loop to.
Oh, that's a good point. That's a fine point. I had been keeping them in my brain as in terms of embedded systems, where you're trying to go after clock cycles. So like, what's the propagation delay through those switches and through the op-amp? Well, it's going to be far less than your clock thing. And in fact, I'd probably say this isn't even medium. This should be like ultra low, because clearly we have to go multiple clock cycles to get anything done. So I should have said that should be ultra, super low. But I would figure that these were all fast in that context of how long do you have to wait for. If we look in contrast like the SAR ADC, right? That one you have to actually converge to a value. So I think those were all fast. What about linearity? This was a trick question because I didn't design it, didn't explain it very well. What do we think? So it gave you a bad test question. What do you think? Not even a guess. It's total like, all right, one brave person.
I said the voltage divider in R2R had high linearity because you're just using the same resistor values across them. Binary weighted was medium to low, and then pulse width modulation I didn't really know what to do with.
Yeah, so I think next time I teach this, I'll go find a little tutorial on how you actually make resistors in silicon, and I think that will help out. So the challenge is making two identical resistors in silicon is pretty good chances that they're going to stay constant, right? So there's not only there's process variation, there's like this polishing step which can like literally round off the corners of your resistors, reducing some of their resistance. There's all these things that give you variation. So they make structures that try to guarantee that two resistors would be the same value if they're exactly the same size. And so that's why here I'm going to say all the resistors are the same size. So the likelihood that there's going to be variation between them is low. But as we go out here, we need to have lots and lots of different sized resistors. And the likelihood that one of them is a little bit off and will affect the linearity of your DAC becomes higher. So that's why I said these are medium, and maybe this one's just a little bit less than the other one. Anyways, that's what I came up with. Yeah.
What is linearity?
Like linearity, like as I go from one value to another value, what's the likelihood that the step size is going to be the same?
Say it again.
Okay. Clearly, I have holes in my teaching. Fantastic. Here we see resistors. What happens if one of those resistors was 99? Then I'd walk through and I'd have this misstep in my DAC outputs. I'd want some value and it would be a little bit off. So that's what we're meaning by linearity. It's not a linear step.
Wait, like all the outputs would then be off?
Well, let's say if I connect just this one, right, in this ladder, one voltage, then that one would be off. If it was the binary weight, then every time I use that leg, it would be a little bit off. That's what it is. Oh, complexity. You guys think, yeah.
So I'm guessing because we're thinking about like we're including the PWM
Yeah.
as part of it, so I would say like that's pretty complicated because you're setting up more stuff. And then for the voltage divider, you have a decoder, so I said it's like a medium because that's just more stuff going on, and the rest I gave low, just because it's like just switches at that point.
That's good. I guess it depends on who's it complex for. All right, is it complex for you as the embedded systems person? As the programmer? That's important, because like the PWM actually requires you to put like low pass filter on the PCB. That's more complex. Or is it from a design point of view, the design of this thing, is it complex? I didn't answer that question. I didn't make that clear. Yep, and then I'm looking at my answers, they don't make sense either. That's fantastic, I have to update them. Somehow I said do not scale, I inherited these slides. Do not scale, does not scale, that doesn't make any difference. Okay, how about power? What do we think from a power point of view?
I figured when you have more resistors for like the same number of bits, then you're like probably wasting more power. So I just ranked them in order of like how many resistors I thought were used, and like I hope my reading comprehension's good. I think voltage divider has the most resistors going on, so that's the highest power, and then the next two like resistor style ones are medium, and then like the low pass filter is probably low power.
I think that's a pretty good argument. I guess maybe I was more thinking in the grand scheme of things, but I think part of this is just providing a good rationale of why you're thinking about things. It's not, clearly I didn't make this as like an absolute, like calculate the power. Ugh, that'd be horrible. All right, how about number of resistors and switches?
I said that for the voltage divider, there's n switches and n plus 1 resistors.
Alright.
For the R2R DAC, there's n switches and then 2n resistors. And then for the binary weighted, it's a 1-to-1 ratio between resistors and switches.
I think of these slides I got wrong then. Let's see. So voltage divider, there is, let's go look out. What did you say? There should be, how many switches did you say there?
Oh, I think you got it wrong. I think you got voltage divider wrong.
Okay.
I said there was n plus 1 resistors and then n switches.
Okay, I think this is right. I don't know. Yeah, so I think that the key here is that you're getting less and less resistors, although that's not the case here with, as somebody pointed out with the R2 ladder. Where did I make a mistake there? Yeah?
The R2 ladder is 2 to the n plus 1 resistors.
What should it be?
Because I think it's just 2n, because if you go look at the design, each branch has 2 resistors on it, and each branch is just controlled by 1 bit, there's no like.
It is 2n. Alright, unfortunately, I cannot, for whatever reason, I cannot actually change these slides on the fly. But I will update them before I send them out. I don't even have paper. Two N.
2n plus 1, because of the additional resistor at the end for the
Yeah.
summing amplifier.
I think the it got raised to the power of instead of and it shouldn't have. Okay. I'll update that before I go out. Okay. Any questions? Yeah.
We explained conceptually the difference between the conversion method of the binary resistor and R2R ladder, because it seems like both of them just divide the ref into increasing powers of 2 and you just sum them. So like, why is one preferred over the other?
It's not powers of 2. It's this one is so this is the R2R ladder, right? And This is the binary weight. So the trick is the resistors, the number of resistors, right? So here I have R and then 2R, double that value. And then here I have less resistors, but I have to make more ratios of those resistors. Right, so here I have to have, before I only had to have 2 resistor sizes. Here I just have to have a resistor that's R and another resistor that's 2R. And that's all, I just have to make that in my design and wire them up. And that's fine, and the fact that I'll probably be able to make those without having a lot of process variation, is pretty high. But here I have to make all these different resistor values and make sure that each one's correct.
But they're both like binary, like powers of 2 being summed together.
Yes.
Okay.
It's just that, I guess you would say the feed network that's generating that current is different. So here the feed network is literally just resistors of different values, and here is the combination of resistors will make different currents. Okay. Any other questions? It's a good question. All right. So you have a DAC on your device. You actually get 2 of them. It's fantastic. So 2 channels outputs. You get 8 and 12-bit modes. As you can imagine, we'll talk a little bit about some linearity issues in a second, but due to these process variations we're talking about, the factories will go and test the outputs. They'll probably test the outputs at like maybe 4 or 5 different DAC values and check to see, do I get what I expect to be getting? And if you're not, then they'll figure out how to trim the values. Basically, they'll record the offset and then put that into a buffer or into a register. And so now you can go look up what is the offset of my DAC so that you at least know what you're outputting. So that's already been factory calibrated in. Let's see, you can synchronize the updates. So if you have 2 things you want to have them at exactly the same time, you can have them output rather than having to do like one and then the next clock cycle the other one. So you can make them have good timing. We talked before with the ADCs, there's different loading modes for data alignment, whether it's left or right aligned. And that's really comes down to if you're going to use DMA or how you're going to load the data into your DAC. What often happens is that you will have this big memory array, and you're basically going to be shoving that memory array into your DAC and playing it out as fast as you want, and you get some control over how the DAC should interpret the data in those memory locations. This particular device has a sample and hold mode, which actually is the kind of opposite of an ADC. So ADC takes the incoming value, samples it, and then holds it. This will do the opposite. It will take the output value, sample, and hold it, and actually can put the entire microcontroller to sleep while it's still holding an analog value out. So it's not always, you don't have to have digital logic doing it. It has a little analog voltage keeper that's going to keep this value out. That may not come into your projects, but it's just a cool thing to know that exists. And lastly, we'll talk about some types of errors in ADCs and DACs in general. We talked multiple times about quantization error. This is the most common inherent. You're never going to get around this. It basically means that the least significant bit, you can argue it is noisy, right? Like there's uncertainty in at least the half of the least significant bit. Other sorts of errors come in offset, right? So there could be some gain offset that slid this entire value over. Maybe the foot resistor on one of your ADCs was a little bit off and it slid everything off to one side or another one. This is easy to calibrate, and this is essentially what STM is doing for you. They're trying to calibrate this out. Another common type of error is gain error, where the whole ladder, the whole conversion process is skewed to one side. This is also, this is something that's harder to calibrate out at the factory, but if you went through and sampled with your ADC a bunch of known values or output DAC values and measured their analog voltage, you could create a transfer function let's calibrate this out. So this is an easy error to deal with. There are two errors that are hard to deal with, and probably it's just good to know that they exist. So differential error or differential nonlinearity is a statement about the difference between bit sizes, and that's sort of what we're talking about with linearity before, where maybe those resistors weren't exactly even, and now on your DAC you have different step sizes. So that's definitely possible, and usually your manufacturer is going to tell you what your differential nonlinearity is. They're going to say, well, we can guarantee it's within, say, one least significant bit. The challenge, and the reason I put this up here, is that sometimes you'll get weird conditions where a resistor will be so bad that you may have a differential nonlinearity that's bigger than LSB. All of a sudden you're trying to put in this value, and now there's two potential, or put this value in, there's two potential analog voltages represent that value. If you have like a 12-bit ADC, you may never notice the difference. But if you have a control loop and you're trying to control something based on that, and now you might find yourself stuck in this local minimum here where you're trying to figure out where to go. So it's just good to know that differential nonlinearity and know the magnitude of it in your system. The other one is kind of related to the gain, is how offset from linear are those steps overall. And so the integral nonlinearity here is a statement of, well, those stair steps, the edges should all be in a straight line, but it could accumulate some amount of error, and it'll affect your transfer function of your ADC. So those last two, integral nonlinearity and differential nonlinearity, are not that important. It's good to know that there are those sorts of problems. The quantization error is inevitable. Can't get around that. Offset error, something you can calibrate for. Gain error, something that you, for each one of your devices, can calibrate for. So maybe I can ask this higher level question, and maybe I said it before. But how many bits can you trust in your system? What is it? You have a 12-bit ADC, 10-bit ADC. How many bits of those are going to be faithfully representing your analog signal? What's your intuition say? Seven of the 12 are good. Okay. 10 of them. Why? What makes you? What are the factors that make you come to that conclusion?
I feel like I usually round. So.
As an engineer, I like that. I like whole numbers. Fantastic. The physicists don't care. They want the precise number, but the engineers, whole numbers. What can we say about the least significant bit in error?
The least significant bit is bad. So like, I mean, you use like the quantization error, and you can just say like however many bits that's worth, just knock it off, and then whatever's left is what you care about.
So that's plus or minus half a bit, right? So already we can probably say the least significant bit is garbage, right? In almost all your systems. Just through quantization. You're going to go through and you're trying to measure, is this signal exactly 12, you got some 12-bit number, is it the least significant 1 or 0? It almost doesn't matter, because you're already, half of that bit is already just garbage because of quantization error. What are some other practical sources of noise in the system that may impact your ADC, let's say?
Can we assume there's always a buffer? Because if there isn't a buffer, then there would be noise from the load.
For a DAC, sure, always assume there's a buffer. It's good. And there wouldn't be, I would have never thought about the load being noisy, but yes, we can assume that that's not a problem. Or some other practical sources of noise that might influence your systems. I'm really nailing this lecture today. All right.
If you have like component values that are a little off from what you assume they are, I don't know.
I think so. Other sources of noise, power supply noise is a big one. And so that power supply noise, So at some point, you guys should just go look, take an oscilloscope out and try and look at your power supply when you got your whole system running, and you'll find that it is actually like plus or minus 100 millivolts easy. And what's the frequency magnitude? Whatever your clock is gonna show up in there as a part of the frequency, your SPI traffic, any of your digital traffic will have all these little spikes in there. So imagine you're trying to sample a voltage that's like 3 millivolts, and your power supply is wiggling by 10 millivolts or 100 millivolts. Like you just don't have the ability, because your reference for that ladder that you made was your power supply. So this is why like you have to think about your entire system's ability to measure this analog value, and it may find that depending on your system settings, the second bit might be garbage, the third bit might be garbage, so you weren't that far off. Or you weren't that far off either. But so I guess just thinking that the impact is your ADC is not some golden perfect Falstad simulation thing. It is immune to noise, or it's impacted by noise significantly, and the first and second bits may just be garbage in your system. Okay. What else are we take, Joe? Okay, fine. All right, so we'll just recap there. Voltage ladder, 3 types of DACs. So the slow pass filter, binary weight, R2R ladder. There's another one that's a sigma delta DAC. It's beyond this course, but this is the 4th kind of one that's often used. We talked about sources of errors. The rule of thumb is the lowest significant bit is noise. I would say in a noisy system, so for any DAC, the lowest significant bit is noise, but for any system, I'd say maybe the lowest 2 bits, depending if it's a high resolution system like 12 bits. Okay, so that is the major content for DACs, which means that's the major content for the course. We're almost done. Monday we'll review for the exam. And then Wednesday we will we'll talk about PCB design and DMA, just so you guys have that background. And I'll stick around for us to talk about your projects or talk about your presentations. We still have classes though. You still have to come to class for student presentations.
To go to 470.
I feel like it matters that much.
That's a good point.
Waiting thing I'm trying to index into.
We don't know what that means.
Power budgeting, is that part of battery management? Like
I haven't looked into DACs.
takes this many watts, like how many hours do we want out of it, or are you looking for something else?
Maybe it turns.
I was thinking about circuits that drew battery man.
Oh, like buck
So-
boost.
I'm just our last
I just wanna go to lecture.
I need to figure out my
like what was it, audio generation?
It's gonna be a linear regulator or a battery pack. There's these other types of things, like so buck and boost converters, so people know that they exist.
There's those really inefficient like chips that like make a lot of heat. You know what I'm talking about?
Yeah, there are. Oh yeah, that would be a linear regulator.
we have it.
Those are linear regulators.
Oh yeah.
And they're basically just voltage dividers. They tell you to burn the current or burn the voltage. You only have one. You want to get into like there's which are hey look, you can buy
We're doing like separate boards.
Like the power boost, those were really good.
this will manage your power. Whoa. This will manage charging of your device. And then there's fuel gauges that will measure how much current is being how much charge is, and it will tell you what your device is.
The LiPo's important too, because if you go too low, you just like kill your battery.
Just how much charge is in there, like knowing that the amount of charge that you
That too. I'll see ya.
there, like there's a factor.
Okay, I'm gonna have to re-up on my 215, but this definitely makes a lot of sense. I feel like this could.
Yeah, I think I wanna
The
do
only reason I'm doing it is because it's an MD.
12 minutes with 3 minutes of questions.
No,
Just
classes you can't take any more classes.
and if it was alright if we could come to you for like some sort of health check.
Oh yeah. Or me or Matt or James, anybody.
That
So,
sounds great because there's some things
Was that like so attack changed from the use and you want to get like a well
Yeah. That's all fine, but like the intricate differences between the three types of DACs we covered.
Alright.
Voltage divider, the R2R.
I guess it's one
Project.
It's fine. I mean, that's the one that I have most intuition from. Okay, maybe the ladder one also. I think else was just like, I don't know how this clear because like you're gonna be adding so many registers just to increase the number of bits that you want to decode.
Pull the project, I would assume that you don't need to have all those colors and you'll be
Duty
fine.
cycle like
The primary colors, right? Unless you really want to go and get DACs in. Your presentation, because there's a lot to talk about with VGA, just to say, hey,
how much you store in the capacitor and resistor like I think helps you like even how fast you're doing it. You basically get these like janky like midpoint like average out values from the current duty cycle that approximates.
And there's like a million and one ways to do it, so I just wanna talk to
Like you don't like
push sensors, like, then I go ask you.
Film is very similar to like what you're trying to do in terms of like
acceleration. I don't even know if that would work.
how do you
The
use
ball, so there might not even be acceleration. And then we can make
yeah,
our
there's
own.
going to be a impulse, yeah.
It might be dangerous.
I mean you use it,
How to weigh the pros and cons.
use the timer for
We have to be experimentation. So you get the ball, you get the glove, you get the things you need, and you're throwing it back and forth, and you go and like these piezo
let's
sensors
just tune the PWM.
set up to oscilloscope. You're just like, can I reliably see it? And one test.
The PWM, what we saw in Falstad basically is
the clock. They can hear it too, but like if you can visually tell on the oscilloscope that you caught a ball, then you can probably
basically is
recognize it too.
Okay, so
and that capacitor takes the average value of the PWM. And so as you vary the square wave,
Well, it should be the frequency, right? So this is slow, and impulse should be fast. So that's a component. That tilt switch, I don't know how that would work. Maybe the piezo would work better.
Alright,
Okay.
I'll look into it. Thank
Yeah.
you. Last time, right? I just wanted to like
how long something's on.
question about pre-lab.
Did it work at all?
Yeah, it's all
You know,
like
yeah, so high
Open up the inside.
cycles how long it's high and low for.
These separate microcontrollers layered on top of one another. It's just the
Do you want me to explain it better?
And we also look at
do you cycle just like
stuff and even
high and then the low? So just a square and then the point cycle.
You just take out all the guts you see for the LED components, and you just like cut everything else off.
okay.
You can do that, or you can put another solution.
It's how
But then at that point, how do we like
I mean how long it, so like
control the LEDs? Because if you put out all the like
same frequency.
Your own way of.
But they're
All I'm pointing out is like, you could go and say like, okay, well, so now what I want to do is I want to put some panels with LEDs in them. And I'm saying just you have free reign to destroy those things, and if you just want LEDs and panels, they already exist for you.
full explain.
Other option then would be like at that point, what would be the difference?
Oh, like I remember
Like figuring out how to connect two LED strips and then putting those on just like a board and then putting like screwing over top of it.
Are gonna be like
They all.
The only
They all.
difference is the mechanical.
Okay, sure.
I'd rather go
Let's
to
say
it's gonna
Is that stuff like would that change
Also,
any
they're
of
gonna
the
stop it
figure
when they
of that or?
I don't remember what we were giving you different. I'd have to look at your projects a little bit, but I don't think you said the displays was the most important.
Yeah, it wasn't, but
So
okay, so in
why
that
don't you
case.
go like the most easiest practical one, and if it's cutting those things and using the raw LEDs and those pixels, nano leaves, that's totally fine with me.
Sounds good, thank you.
Okay.
There's a couple values to bring.
I spoke with you
how do you use a timer to
about me being out of town for the second exam. You said I could take it the Monday.
There's normally like 3.
It's a cure for me checking in to make sure.
That's good that you told me because I forgot.
Yes, so I mean, gets rid of it, gets enough of you, or we can take that.
It's like a mini here.
We can, let's figure it out for the next week. Why don't you send me an email? I'm pretty behind in emails, but just say
Only digital logic.
E373 exam accommodations, and then I will.
We got it in parallel.
Go up. See how we can create different outputs?
Yeah.
On the
Legitimate.
duty cycle of the timer.
Yeah.
This is how it works in theory.
Let's build
so
a
it's
big
like, I was planning on taking
I'd
473 like
say it's a longer exam,
Okay.
but it's good to take both levels. This is definitely sitting like OS.
Like the capacitor takes the average of the duty cycle.
So what do we teach? So it's
Capacitor takes the average of this.
there's reading papers
Okay.
and like trying to understand the history of like how did we start making things like augmented reality glasses, touch screens, like how does
That's how we're gonna
the history of ubiquitous
sound like this charge of the capacitor.
the mouse come from?
Okay.
Like why do we choose a mouse at all? And like there's some of that, and then the project-based parts are like 3D printing, digital fabrication. So there's units. There's
Hypothetically,
the neuter set. There's
to like something like
talked about, but then mostly it's like you design and pitch, you pitch and design a product. And you build it, do that, and build it again.
Cool.
Yep.
Quick question, for the so we just like have something we're filling out, we'll go into all of them.
Yep.
I might miss one of them, but I think
Our class participation grades.
okay.
So I've seen you here many times, so I feel like you're not.
No, I have not missed a single lecture so far. But then I was like, oh, presentations, yeah, I can miss all of those, but it's fine.
Right, because then I know you're gonna do that, so that's why I make everyone grade them.
Yeah, I think, fine, I have so far been,
now we have this absolutely ridiculous
this next one.
clock and this ridiculously sensitive capacitor. So when we change the duty cycle, notice how quickly it's able to respond. You see?
Okay. You guys need anything?
Working on lab.
The capacitor
What's lab this week? ADCs.
being able to like, you notice how like when I bring it all the way down, it took time to discharge all the way. But because I made the capacitor so small with such a high clock cycle, it's able to reflect the change almost immediately. So you can get an incredibly sensitive
He's explaining him
output
how EWR
just based on the switching of the duty cycle. And I'm just changing a discrete value here. I'm changing this number up and down. Like it's reflected by this value here, C54. So like I'm changing it by integers. Okay, so you can get it. It's cool. I like it. This is my favorite one.
Wait, so this can be used as a DAC?
Yeah. No, wait. DAC, yeah. Yeah, that's what it's used for.
And then how is it different from the pulse width modulation?
It's a, I forget the exact name. What's it called? PWM?
plus RLC.
Yeah.
PWM filter?
Yeah, okay, so it uses PWM. Like this duty cycle is
RC
a synonym for pulse width modulation. You're, like the PWM, there is no thing you point to and say that's a PWM. You are doing the process of PWM. You are modulating it stands for pulse width modulation. You are modulating the width of the duty cycle pulse. Through
Remember
this.
from timers? We made you do that?
Yeah.
It was great.
Actually, that was pretty fun.
This is my favorite one because you can make it so small and look at how
I know.
it's
It
so
makes you
good.
happy.
It
doesn't
makes me so happy.
I know.
I'm only gonna use this. I don't care. It's the only one I understand.
I was like the last DAC we covered in which we like added a resistor for every additional bit we want to add.
Yeah.
I thought that was like a very neat solution to like scalability.
Yeah.
Because like we exponentially grow with just one resistor.
Exactly.
But then like the R2R one, like and the voltage bridge, they almost had the same resistors.
Yeah, especially for small bit values, but
Like does R2R also like scale decently fine?
I think if we look, I'll have to update I'll double check the scaling factors, but I think it's 2 to the n versus just n. So there's an increase. There's a benefit to R2R.
But linearity would be bad because we are making R type resistors and 2R type resistors instead of just R's.
Yes. So it's exactly. So there's a trade-off, right?
Oh.
And then it even gets worse when you go to you know, binary weight, cause now you need all those different
To
versions.
be different, yeah. Oh, yeah, this is better. Okay, sounds good. Great job.
Okay,
Yeah.
great.
Thank you, Professor.
Thank you. Eat this lab.
Oh, also one last question. For the revised proposal, like how much revision do we need?
Whatever you need to say it's done.
One final question. Is this hair good? I think it's good.
Oh my god, it's great.
Yeah, you see, it's good hair.
Look how much less I have. I used to have a lot of hair. Now I'm getting less hair. That much hair?
He's
That's
insecure
fantastic.
about it, but it's good hair. I'm sorry.
I wanted long hair.
I used to have, well,
I FaceTime my dad, he's like, oh, you're going to here.
You all support that database,
Yeah, I signed an offer with them.
so they don't mess with you.